Now that we know what differential equations are, the next thing we're going to do is we're going to learn a new type of a differential equation, and for each type we will learn how to solve it, and after that we will discuss some applications of that type of differential equations. And in this lecture, we will learn a new type of differential equations that's called separable differential equations. And we say a first order differential equation is separable if it can be written in the form in which we have a derivative on one side and a product of two functions on the other side. But the two functions on the other side, one must be only the function of x, and the other one must be the function of only y. So, for example, y prime equals x squared times y is an example of a separable differential equation. Why? Because I can clearly identify my function of x, which is x squared, and my function of y, which in this case is y. On the other hand, you can look at this equation where I just changed the multiplication to addition, and now there is no way you can figure out what your f of x or in g of y would be, so that the product of the two is equal to x squared plus y. It is impossible. So therefore, this is not separable. And this one is. So let's do a couple more examples of separable and not separable. I suggest you pause here before you answer the question, but tell me, do you think this is separable or not? And the answer is yes, because we can factor out x squared, and then we'll end up with a function of x squared and a function of y 1 plus y. So this is separable. Now let's try this example. We have y prime 2xy plus 3y minus 4x minus 6. And the question is this separable or not? And the answer is actually yes. Why? Because we can factor out y over here, negative 2 over here, and factor out 2x plus 3, y minus 2, and the answer is it is separable because it is the product of a function of x, 2x plus 3, and the function of y, which is y minus 2. So the question is now, how do we solve separable differential equations? And let's consider this example again. So what can we do here? And let me note that this equation is written in Newton notation. for this, we use little apostrophes to notate the derivatives. Um, Alternatively, we can use Leibniz notation. And in Leibniz notation, this equation can be rewritten as dy dx equals x squared times y. And the method for solving separable differential equations implies the following manipulation. It is going to appear that I'm moving dx here on the right side by multiplying both sides by dx, but again, remember, this is not a division bar. So technically, I am not multiplying here, but it totally looks like it. So what we're writing here on both sides of the equation are called differentials, and they are covered in Calculus 1 class. However, I would also like to move this y over here, and now it is a division. So we can do this two operations at once. I can move y on the left, dx on the right, and again, it totally looks like I multiplied by dx, but I did not. However, the next step will make it more sense out of this equation. Now, since both sides appear to be equal, it totally doesn't violate any laws if I take the integral of both sides. And now both expressions on both sides actually make sense, and setting them equal to one another actually does make sense. And now that it all makes sense, we proceed with integrating both sides of this equation. So on the left side, we have a natural log of absolute value of y, and on the right side, we have 1/3 x cubed, and technically you would add a constant here and a constant here. They will not be the same constant, but in order for us to, instead of having two constants, why don't we just have one constant? And you can pick the side, whichever you like, to add that constant. So what we have here now is the general solution of the original differential equation. However, it is in implicit form. So what does that mean? That means the y is not isolated. So technically we solved it, because at this point we don't really care if your function is written in implicit or explicit form. However, frequently we would also like to write this solution explicitly. However, again, I just want to emphasize this. It requires an additional step. So let's take our general solution and let's write this in explicit form. So in order for us to write implicit equation explicitly, we have to isolate the variable y. And we're going to do that algebraically, and we're going to perform whatever operations but on both sides to maintain the balance. And first thing I'm going to do, I'm going to exponentiate both sides with base e. So e to the ln absolute value of y is the same as e to this power. And on the left hand side, we e and ln cancel each other. as long as the absolute value of y is in the domain of the operation. And on the right side, we are going to use the following property of exponent that allows us to break the exponent. When you have the sum and the exponent, we can break it into the product of two exponential expressions like this. So we're going to use this property, and instead of having e to the power 1/3 x cubed, we're going plus c in the power, we're going to break it up like this. And here I'm going to do the following. Because we're going to have a lot of these c's floating around, so the first c that I actually have, I'm going to call it c1. So this original c right here, let's call it c1. And here I have e to the power c1. But guess what? E to the power c1 is just another constant, so why don't we just call it c2? And instead of having e to the power c1, I can just write it as c2 times e to the power 1/3 x cubed. Now we have to isolate y by getting rid of the absolute value. So absolute value of y equals something implies that y inside could be equal to plus or minus whatever that right hand side we have. And this time, again, we have control over the constants. So instead of writing plus minus c2, I would like to write it as c3, but since this is my last constant, I'm just going to call it c. And we isolated y. So what we have here now is the general solution, but it is now in explicit form. So this will make everybody's happy. Alright, so as we know, we can easily obtain a particular solution from a general solution when initial condition is given. So let's solve quickly this initial value problem. So let's recall that the general solution that we obtained previously was c times e to the power 1/3 x cubed. And to find the particular solution, we're going to use the initial condition, and we're going to replace y with 1 and x with 0. And we're going to solve for c. C is equal to 1, so we have a solution of this initial value problem. Y is equal to 1 to the, times e to the power 1/3 x cubed. So we did solve this initial value problem. Let's do another example. Let's solve this differential equation. So we're going to follow the steps. The first step is to isolate the variables after we use the Leibniz notation instead of Newton notation. Again, visually it appears that I'm multiplying both sides by dx, but I'm not. But I am going to divide by y minus 2, so we're going to have 1 over y minus 2 dy equals 2x plus 3x. And again, it doesn't make sense until I put the integral sign here, and now it all makes sense. And we proceed by integrating both sides. Here we have ln of absolute value of 1 minus 2, and here we have x squared plus 3x, and we only need one constant. So again, I'm going to call this C1, and this is implicit form of my solution. Frequently, we want to have it, this is implicit, so frequently we want to have it in explicit form. So we continue here by exponentiating both sides, and as previously I showed you, this C1 becomes C2 in the front. To get rid of y minus 2, I guess let me do this on the side here, because these steps are technically, they have nothing to do with differential equations. This is just us writing, turning the general solution from implicit form to explicit form. And we're going to get rid of the absolute value. And instead of plus minus C2, I'm just going to write C3 here. And we're going to add 2 to both sides. And since this is our last constant, we're going to just use C instead. So the final answer is y equals c e to the power x squared plus 3x plus 2. So this is the general solution in explicit form. Now, if we had some initial condition given, we could use it to solve that initial value problem. Alright, let's do another example. Let's consider this problem. And this time let's make it an initial value problem. So let's assume that y of 2 is equal to 5 over 4. So first step is to separate. So we're going to separate it by rewriting Newton notation and goodness notation, and then rearranging. So 1 over cosine squared y goes on the left, 1 over x squared dx goes on the right, and after we put the integrals in there, it all makes sense. On the left side we have integral of secant squared, which is tangent y. On the right side we have integral of 1 over x squared, which is negative 1 over x, and we only need one constant. And again, this is the general solution in implicit form. And if we want to turn implicit to explicit, we have to isolate y, and we can do that by, in this case, let's see, we have to be careful here. So tangent y is equal to that, so we can try to isolate y by applying arctangent, but we have to be careful because arctangent is only defined on the interval from negative pi over 2 to pi over 2. And since pi over 4 is in that arctangent is not defined there. The range of arctangent is pi over 4, from negative pi over 2 to pi over 2. So, and since in this case the initial condition is in that interval, that means it is appropriate for us to uh, apply arctangent to both sides. So, taking this back here, we conclude that y is equal to arctan of -1 over x plus c. And now we're going to recognize that we have an initial condition here, and we're going to use this initial condition to find c. So again, let's take it on the side. To find c, we're going to replace x with 2 and y with power 4. And now when it comes to this step, it actually doesn't matter which of these two equations you use to substitute and find c. So right now we're trying to substitute into the second one. However, it could make more sense to do that in the first one. So either way, you should get the same answer. So anyway, let's take tangent of both sides. So tangent of part 4 is equal to -1 half plus c. So since tangent of part 4 is equal to 1, c must be equal to 3 halves. And we take that back here. So we found a particular solution. Y is equal to arctan of 3 halves minus 1 over x. So this was our general solution, and this is a particular solution that solves the initial value problem. And let's do one more. So this is also an initial value problem, and we're going to identify this as a separable equation. So dy dx is equal to 4x e to the -2y, and we're going to bring e to the 2y on the left, dx on the right, and it all makes sense after we throw the integral symbols in there. And on the left we have 1/2 e to the power 2y is equal to 2x squared plus c. So this is the general solution in explicit form. So let's call this C1, and let's put it explicit, implicit, and let's rewrite this equation from implicit form to explicit form by isolating the y. So first thing we're going to do, we're going to multiply everything by 2. And instead of 2c1, we're going to call it c2, and then we're going to take natural log of both sides. So 2y is equal to ln of 4x squared plus c2, and then we are going to divide this by 2. And we can move that 1/2 inside of the logarithm as a radical. And since c2 is our last constant, we can make it our c. So let's take this back over here. Now we still have our general solution, but now we have it in explicit form. And one last thing is we need to find the particular solution that satisfies the initial condition, and we're going to do that by plugging in 0 for x and ln2 for y. And 4 times 0, so square root of 4 is 2, so c must be equal to 4. And now we have our particular solution. So 5 plus ln of radical 4x squared plus 4. So this is the particular solution that solves this initial value problem.